Shalom everybody, welcome to IMEC 14 and to the first session on nanomaterials and nanotechnology. It's a new experience to me to co-chair a session, so we'll see how it works. Anyway, the first speaker is my co-chairman, Professor Reshef Tenne, who is well known for the invention of inorganic fullerenes and top scientist in applied and basic science of those technologies. Reshef, please.
Thank you, Ori. First of all, I would like to congratulate Noam Eliaz and Ilan Golfar for raising up this beautiful venue. I think it's a great success, and I think that this tradition is a very important tradition which should be continued. What I'm going to tell you a little bit about is a progress report of what we are doing in terms of the synthesis of new inorganic nanotubes and study their properties and eventually some applications of these nanomaterials. So the idea is, as you know, or those that heard me before, is that we wish to construct nanotubes from layered compounds, from inorganic layered compounds, and I don't know if there is a laser pointer. There must be a laser pointer around, yeah. So as we do that for graphite, we want to do that for molybdenum disulphide. I've shown this slide many, many times, so I won't be able to show it again in the short time that is allocated to me. Anyhow, the edge effects, which are prevalent in this kind of structure, there are always molybdenum atoms which are only 4-fold bonded instead of the bulk atom which are 6-fold bonded, and therefore the structure becomes unstable in the nano regime. And once you understand it, you can try and synthesize nanotubes and Fullerene-like structures from inorganic compounds with layered structure. And that's what we did. And here's an example which I show often, but there is always a progress in this slide. Namely, we started 18 years ago, seeing these kind of closed structures of molybdenum and tungsten disulphide, which were produced in minute amounts and dispersed in a lot of other material. And today we are able to produce as much material as we wish, not as pretty as this one, but not that bad. So this is molybdenum disulphide nanoparticles. It's only a question of putting more effort and putting more money in order to being able to produce this material in large quantities. Anyhow, what you see here are closed structures of molybdenum disulphide in contrast to the well-known platelet form of the bulk material, which is basically a deck of cards. And you see that each nanoparticle is made of numerous layers, and they are not perfect, there are dislocations, but they are all closed structures, and we can do pure phases of this material with very good control on the purity and on the closeness of this structure without a single nanoplatelet or platelet in the entire structure or in the entire bottle. So we do that by looking, for example, I show you a recent publication where we have produced the molybdenum disulphide from molybdenum oxide. This is something that we already did 16 years ago, but now we can do that in large quantities or at appreciable quantities. And what we do, we take molybdenum oxide, we evaporate it, and then we flush it with hydrogen. The vapor of molybdenum oxide reacts with the hydrogen, reduce the molybdenum oxide to molybdenum suboxide, which loses the vapor pressure, forms nanoparticles of molybdenum oxide. These nanoparticles then react with hydrogen sulfide around this position, and then in a matter of seconds, they are covered by 2 layers of molybdenum disulfide on top of a molybdenum oxide core, and then they land on the filter here on this pile, and they gradually, by a diffusion control reaction, convert from molybdenum oxide to molybdenum disulfide. They grow quasi-epitaxially inwards, the sulfur diffuses in, the oxygen diffuses out, and they grow layer by layer until they form this closed structure, which is made of molybdenum, solely of molybdenum disulfide nanoparticles. In the case of tungsten disulphide, the reaction is fairly similar, but it's more easy to control because we don't have to evaporate. We simply take tungsten oxide nanoparticles and we do the same reaction. And therefore, the reaction with tungsten sulfide has gone further in terms of quantities. We can make now these nanoparticles basically in tons. It's just a question of price. Nevertheless, I have to mention it's not a trivial reaction. The reactions are known since many years, but the exquisite control of the size of the nanoparticles is the key issue here, because once they grow above 200 nanometers, they won't form any more closed structures like this. So recently we were able to make them, to dope them. We use different methods. We can dope them now in different techniques. So in this case, we dope them with rhenium. We dope them also with niobium. And the idea here is to introduce minute quantities of rhenium in order to make these nanoparticles conductive. And so we can now make rhenium-doped nanoparticles. You see, they look the same, but they have a fraction of a percent of rhenium into the structure. The rhenium substitute for molybdenum. Since rhenium has in its valence electron one extra valent electron, it donates this electron to the conduction band, and the material becomes extremely conductive. So this is the resistance versus temperature. This is the pristine material, and when we dope it, it becomes like that. I won't be able to elaborate very much on the doping process. Some of it has been published, but the more recent work is not published, and we are not able to describe in detail the reaction, the growth process. Nevertheless, it comes very close to the calculation. The calculations were done by Professor Seifert and Andre and Yash in Dresden, in the Technical University in Dresden, and they calculate the rhenium doping of molybdenum disulfide nanotubes, and you see that the donor level, which is here, this is the donor level, it's only a few hundred millivolts from the conduction band, and that's more or less the same energy, activation energy, that we found for the donor level in the rhenium-doped molybdenum disulfide nanoparticles. We can also dope nanotubes using a similar strategy, and we can get highly conductive nanotubes. Once you have this, you can do a lot of other things that we weren't able to do so far. The production has gone to large scale 2 years ago, and the material has been commercialized last year. The quality of the material is not the same as the one we produced in the laboratory, but nevertheless, we can produce it now and in large scale using a fluidized bed reactor. And you see the progress over the years, and you see that we can make it now. We can make products from that, and the company Nanomaterials, which licensed this technology, is now producing variety of lubricant. So I didn't mention it before, but as you well know, this material is very good lubricant, and because we thought initially that it has a rolling friction element there. I'll come to that point in a minute. It's much more complicated. The lubrication mechanism is fairly complicated. The work has been done jointly with, initially with Professor Lev Rappaport, with whom we collaborate a lot until these days. We also collaborate with other groups, as shown in this slide and in other slides. So this is a commercially available lubricant now, and this is a work that has been published recently together with the group of Fabrice Dessanoy in École Centrale in Lyon, and it shows that these nanoparticles indeed are very good lubricant. And you see the low friction coefficient under 1.4 gigapascal. A friction coefficient of 0.03 is extremely low, and it shows that this material has a big commercial potential in terms of lubrication. So there is now a large, two large projects, European projects, combining industry and academia to make to use these nanoparticles as a replacement to additives that exist already in the oil industry. As you may know, the oils that have now additives which are not environmentally benign, and they have to be replaced in a matter of few years. And one of the solutions, or maybe the premier solution now, will probably be to replace the additives, the current additives, with these nanoparticles. So this is an ongoing research and development effort in another direction that has started a few years ago, just 3 or 4 years ago, not more. These nanoparticles are now added to a variety of polymer composites, making nanocomposites with enhanced mechanical properties. And you can see here a recent work published by a group in Spain, where the mechanical properties have been tremendously improved by adding very small amounts of 1% of the nanoparticles, IF nanoparticles, into the polymer, which is in this case polyphenylene sulfide. There are a number of polymers now that are being investigated and developed. Each one has a different mechanism. The strengthening mechanism is not clear as yet. Of course, there is a chemistry. There must be some chemistry ongoing between the nanoparticles and the polymer. But this problem has to be elucidated in greater detail. Anyhow, you see the nanoparticle and you see the crystallization around this nanoparticle, so it serves also as a nucleation catalyst for the polymer, for the thermoplastic polymer. And this is a recent work which we have, which is now in press basically, joint work with Professor Hannah de Duke and Sam Kenning at the Shankar College. The student Mark Schneider did a very beautiful work where he added these nanoparticles to thermostatic polymers, to epoxies, and show tremendous increase in both modulus and the peeling strengths of the polymers. These are air quality or aerospace quality polymers. And he furthermore showed that using FTIR that a new SOC bond is formed between the polymer epoxy group and the outermost sulfur layer of this polymer, of this nanoparticles, sorry. I want to show you now a research into, by Ofer Tevet, a student in my group, who's is doing beautiful work on the, I hope it works, on the measuring the mechanical properties of individual nanoparticles. I hope I'll find this movie. Okay. Now I have to. So you see the cantilever, AFM cantilever within the electron microscope compresses the nanoparticles until the nanoparticles break down. And in this case, the force that you have to apply, or the load that you have to apply, is about 3 gigapascal, which means that the nanoparticles are extremely robust against failure. This is important in terms of using them as lubricant, because now we start to understand the properties of these nanoparticles individually. And of course, when you come to a group of nanoparticles on the surface, they are entrapped, and therefore their mechanical behavior may be different, but nevertheless, it still shows that when they can behave a very good nanoparticles which withstand a very high pressure and load. This is another experiment which is in progress now by Ofer Tevet, and here we demonstrate rolling friction. Basically, you see that the nanoparticles under the cantilever rotates as we go from right to left, and we build now, or Ofer built now, a very sophisticated measuring device to measure the shear forces, and so we will be able to calculate the friction coefficient of individual nanoparticles, and thereby allowing to learn about the shearing or the rolling friction of individual nanoparticles. So I hope I'll be able to show you the movie somehow. So it's the movie. Okay. Oh, no, it didn't work out. So you can see the nanoparticles. The nanoparticle is not only loaded, but it's sheared, and there is a very nice shearing process and rolling of the nanoparticles, and some sliding too that occur in this case. When the nanoparticles are entrapped in the contact area, it's more difficult for them to rotate, but nevertheless, they can do some of their rotation, and they can benefit from their regular spherical shape. Let me go now into the nanotubes. And the nanotubes have been observed at the same time that the nanoparticles have been observed. And now you see the perfect nanotube. We now know for the tungsten disulphide there are two growth mechanisms. One growth mechanism which gives rise to very narrow, slender nanotubes with about 5 to 10 layers, 20 nanometers in diameter and about few microns in length, very perfect in shape. And another growth mechanism which I won't have time to show, allow us now to synthesize large amounts of these nanotubes. And you see here the first kilogram of nanotubes that has been recently produced by Dr. Alazak and Menachem Genut in the company, in nanomaterials. So by controlling very carefully the growth conditions, they could now produce a large amount. There is no barrier now to grow these nanotubes in large amounts. And you see these nanotubes are, they have more layers. They are a bit thicker. They are about 30 to 50 until up to 100 nanometer in size or in diameter, but very long and very strong and very perfect in shape. And therefore, their mechanical properties are very desirable for many, many applications. So this is actually a study that we have published jointly with Dr. Maya Bar-Sadan, who is in the audience or might be in the audience. She finished her postdoc in Jülich in the laboratory of Knut Urban, who is the speaker tomorrow, plenary speaker tomorrow. And using the CS-corrected, aberration-corrected microscope, you can see now the detailed structure of the nanotubes. You can see the atoms, the well-arranged atoms, sulfur, tungsten sulfur atoms. You can calculate she has been able to calculate the structure, the chirality of each wall among these multi-wall nanotubes and infer the growth mechanism of these nanotubes in a very exquisite and precise way. And this is a tremendous advantage of using such high-resolution electron microscope to unravel the growth mechanism of nanoparticles. So if I'm allowed, if I will be able to show you their properties, perhaps this is, I think, the last movie that I want to show you, is the marvelous mechanical properties. That's not the best movie, but nevertheless, that's what I found. So you see that you can compress them and they will never break. They are so exquisitely controlled. The synthesis is so exquisitely controlled that basically they have no single defect, and therefore they can be bended and folded without any failure. And you can do that as many times as you wish, and you can, statistically, you find that all the nanotubes behave more or less the same way. More recently, we have published jointly with the student Weizmann a new approach to synthesize new nanotubes using the tungsten disulfide nanotubes as template. So now we take the tungsten disulfide nanotubes and using the simple reaction with lead iodide. There are a few reactions that we can do. The simplest one is simply to melt the lead iodide in the presence of the nanotubes, and by capillary forces they go in and they solidify and they wet the surface and they form nanotube with this nanotube. So the idea here is that you can use the nanotube, the existing nanotubes of tungsten disulfide as template, and we can get now a lot of new nanotubes which we were not able to grow before due to this structure. And hopefully in the future we shall be able to synthesize them in larger quantities, study their properties, and see interesting application for these nanoparticles. And a recent study that has been submitted now jointly with the group of Seifert it shows very nicely the stability curve of the nanotubes versus the nanoplatelet. So you compare the stability of lead iodide nanotubes in single-wall molybdenum disulfide nanotube compared to platelets, and these are the curve for the red curve is for the platelet, and the black curve is for the nanotubes, lead iodide nanotubes, and you see that at a certain point about 60 angstrom in diameter, the nanotubes become more stable than the platelet form, and you see it very nicely here in this picture. So when you go beyond the diameter of about 4 nanometers, the nanotubes become more stable than the platelets. So here you have a smaller constriction of the core, inner core. You have platelets at larger, when the core becomes larger, the nanotubes are preferred. So this shows that we can compare quite quantitatively between experiments, see the comparison between experiment and theory, and get very good agreement between experiment and theory. And once you have this idea, you can try other nanotubes, and indeed we have observed this different other iodide nanotubes which were templated into the tungsten disulfide nanotubes. And we also did gas phase reaction, and we were able to grow molybdenum disulfide either inside or outside or both, on both sides of the tungsten disulfide. So we start to get superstructures, and that gives rise to a lot of interesting possibilities to do interesting physical measurements on confinement and on various other aspects which I will not elucidate at this time. An interesting, very interesting project that had been published recently by the group of Tenne is to synthesize tin disulphide nanotubes by VLS process. VLS process is well known in the literature since many years, and we and others have attempted to grow nanotubes, inorganic nanotubes, using VLS process. Those of you that know the field know that Charlie Lieber from Harvard was the first to show that he can grow continuously or in a very controlled fashion nanowires of various materials using VLS process, a catalyzed. And this is the first time that nanotubes, inorganic nanotubes, are grown using a VLS. In this case, it's tin disulphide with bismuth as the catalytic nanoparticle. And this, of course, gives rise to a lot of opportunities in terms of growth of new nanotubes. In another study that we undertook together with Professor Ernesto Joselevich, we have studied the mechanical behavior of the nanotubes. Basically, what you do, you use nanolithographic method, and you apply a pedal, gold pedal, on the nanotube, and you can use then an AFM to press on the pedal and see the progression of the torsion of the nanotube. And indeed, you see that they really do not fail. They are very elastic, but at a certain point, they have some kind of a catastrophic event, and that actually is not an inelastic or a plastic deformation. It's just a shearing of the outermost layer of the nanotube on the inner layers of the nanotube. And that has clearly been demonstrated by a combined theoretical and experimental study. So in this case, when you go to a very high angle, simply the outermost layer on which you basically compress, this is the outer layer, is detached from the inner layers and starts to rotate freely. And you see afterwards a series of such events also of shearing of the outermost layer. How much time do I have?
So we'll have to adiabatically break your lecture in 2 minutes.
Okay, I will just end up by saying this to show perhaps this picture, because this picture is very significant. As early on we identified, we analyzed the structure of molybdenum disulphide, and we concluded that pentagons are not favorable, and therefore the structure of the smallest hollow closed structures of molybdenum disulphide will not be like the C60, which is made of 20 hexagons and 12 pentagons. Instead, they are made of rhombi, corners which are made of 4 atoms, and a large number of molybdenum and sulfur atoms. This is a bigger structure than the C60. Usually it's about 10 times larger in terms of size and in terms of number of atoms. And indeed, if you look at this structure, it consists of about 600 atoms of molybdenum and about 1,200 atoms of sulfur, and it's made of octahedra. And again, using CS-corrected microscopy and a quantum mechanical calculation by Gotthardt-Seifert, you can superimpose the observed structure on the calculated structure, and you see a very good agreement between the two. So this is the superposition, and I think that with that I would be able to conclude my talk. And I think, to summarize the things at the state of the art, we are now able to synthesize a lot of new nanotubes. We basically, every few months, we and others come with new nanotubes from layered compounds, and more recently from non-layered compounds. So nowadays, basically, if you are a smart chemist, you can go, solid-state chemist, you can go and synthesize nanotubes from any compound and basically get interesting new structures which have interesting properties, and you can do a lot of new observations with this, with these new nanotubes or new nanostructures. And I think that it has a bright future, provided we will have enough chemists that will be willing to undertake this effort to synthesize these new nanoparticles. Thank you for your attention.
Thank you, Reshef. We'll take 2 short questions, if there are. Okay, if not, thank you again, Reshef. And we'll call